Module 5, Part 2, Confidence Intervals. We'll continue with Objective 2, Interpret a confidence interval for the population mean. As we said in the previous video, the margin of error depends on three factors: the level of confidence, the sample size, the standard deviation of the population. We will now take a closer look at how these factors influence the margin of error. Level of confidence. As the level of confidence increases, the margin of error also increases. If we have to be really sure of our estimate, we want to widen the interval to be sure we don't make a mistake, and we want a high confidence level. For example, if you have to toss a paper wad into a trash can without missing, you would prefer one with the widest top possible so you would have a better chance of making your target. Sample size. As the size of the random sample increases, the margin of error decreases. Generally, bigger sample sizes are better, but they cost more in both time and dollars. Researchers have to make a compromise between how big a sample they can use and how much money they can spend conducting the research. Standard deviation of the population. The more spread there is in the population, the wider our interval will be for a given level of confidence. This is pretty self-explanatory. If the data is really spread out, we'll have a bigger standard deviation, and you would expect the confidence interval to be wider than more compact data, which would have a smaller standard deviation. The shape of the distribution of all sample means will be normal provided the population is normal, and we'll have the mean of the sample distribution equal to the population mean, and the standard deviation of the sample distribution equal to the population standard deviation divided by the square root of the sample size. Note the estimate for the population mean is the same as the sample mean, but the standard deviation for the sample is adjusted using sample size. We've encountered this in the previous module. The shape of the distribution of all possible sample means will be approximately normal if the population is not normal, and we've encountered this before. But if the sample size is large, and it doesn't have to be huge, just a sample greater than or equal to 30, then we have that same condition. The mean of the distribution of means is equal to the population mean, and the standard deviation will be equal to the population standard deviation divided by the square root of the sample size. We also discussed this irrelevance of the normality of the population to the normality of the distribution of the sample means in the previous module. Because x bar is normally distributed, the sample mean is normally distributed, we know 95% of all sample means lie within approximately 2 standard deviations of the population mean mu, and 2.5% of the sample means lie in each tail. So this is the same normal curve we've been dealing with. The graph to the right is just rounded to whole number standard deviations from the mean of 0. Because we were using it to approximate, it's easier to say plus or minus 2 standard deviations than it is 1.96 standard deviations. But now we're going to use the 1.96 value. So 95% of all sample means are between the population mean minus 1.96 standard errors and the population mean plus 1.96 standard errors or standard deviation of the sample means. And 2.5% of all sample means will lie in each of the left and right tail regions. So 95% of all sample means are in the interval, and this is just the mathematical way of writing this, the mean plus or minus 1.96 times, and remember the standard error was the population standard deviation divided by the square root of n, so they've just made that substitution. With a little bit of algebraic manipulation, we can rewrite that inequality and say the true population mean is between the sample mean minus 1.96 standard errors, and notice now we're using the symbol for the standard error, which we know is equal to the population standard deviation divided by the square root of n, and the mean plus that value. And the common way to write a confidence interval is to use plus or minus. And when you see that, you split that apart into the mean plus and the mean minus. This is just math shorthand for writing that. So usually a confidence interval is written as whatever your point estimate is, and in this section we're just looking at means, plus or minus your margin of error, and that's how you come up with a confidence interval. Software calculates confidence intervals easily, and this is a program called StatDisk. It used to be free on the internet. If you Google it, you may still be able to find it as a free download. Minitab was used to simulate obtaining 30 simple random samples of size n equal 8 from a population that's normally distributed with a population mean of 50 and a standard deviation of 10. What we're doing in this example is trying to justify that what we're saying about the 95% confidence intervals and the 99% confidence intervals is really true. The computer has the whole population in this example, and it took 30 simple random samples of size 8, and it calculated the mean and the standard deviation and the confidence intervals for all of those to test and see, are we really going to get 95 confidence intervals that contain that true mean of 50? So on the next two slides, you will see those 30, 95% confidence intervals that the Minitab computed for each sample. How many of those samples result in intervals that contain a mean of 50? Well, if there are 30 samples, 95% of those would be 28.5. So since it's a fraction, we know we're not going to get 28.5, but there should just be 2 or 3 of those intervals that don't contain the true mean if all of this theory is correct. So here's your first 15 confidence intervals. You can see the second column here tells you the means, and the confidence intervals, I don't know why the spacing is that parenthesis so far out, but those are your confidence intervals. And the only one on this slide that doesn't have a confidence interval that contains what we know is the true population mean of 50 is this one, sample 8. And then the other 15 are here, and again there's only one sample where the confidence interval doesn't contain what we know is the true population mean, in this case, of 50. So that's pretty much what we expected. Note that 28 out of 30, or this would be 93%, of the confidence intervals contain the population mean mu equal 50. But if you do 95% of 30, you're going to get 28.5, and that wouldn't be possible. In general, for a 95% confidence interval, any sample mean that lies within 1.96 standard errors of the population mean will result in a confidence interval that contains mu. And remember, standard error is the standard deviation for your distribution of the means. The standard error is that value where we take the standard deviation of the population divided by the square root of the sample size. Whether a confidence interval contains the actual population mean depends solely on the sample mean x bar. And if you go back and look at those samples, you'll see the two that did not contain it were the two that had the largest mean. The two random samples that had the largest mean gave us confidence intervals that did not contain the true population mean. So whether a confidence interval contains the true population mean depends solely on the sample mean x bar. A 1 minus alpha % confidence interval indicates that if we obtain many simple random samples of size n from the population whose mean mu is unknown, then approximately 1 minus alpha times 100% of the intervals will contain mu. Now most of the time when we're doing statistics, we're not going to know the real population mean, but we know from mathematics that this is going to turn out that way. And remember this 1 minus alpha, remember you could have an alpha level of 0.1, 0.01, or 0.5, and that would give you confidence levels of 90%, 0.1 would be 99%, and 0.5 would be 95%. So remember, those are just that 1 minus alpha. Those are just telling you your 90, 99, or 95% confidence levels. For example, if we construct a 99% confidence interval with a lower bound of 52 and an upper bound of 71, we would interpret the interval as follows. We are 99% confident that the true population mean is somewhere between 52 and 71, and we write the confidence interval as an interval. Using the sample below, a 99% confidence interval about the population mean weight in grams of pennies minted after 1982 was found to be 2.452 to 2.476 grams. Interpret this confidence interval. With a sample size of 17, we are 99% confident that the mean weight of pennies minted after 1982 is between 2.452 and 2.476 grams. Keep in mind this sample size and this confidence level because we are going to look at this example again and do different confidence levels and different sample sizes. So we're 99% confident that the mean weight of pennies minted after 1982 is between 2.452 and 2.476 grams. How might a bank use that information? If a roll of pennies is weighed and the average weight is much greater than 2.476 grams or much less than 2.452 grams, they would likely unroll and count the pennies, or maybe not since it's pennies, but you get the idea that they would have a suspicion that that might not just be all pennies in that roll. Such intervals exist for other coins and in fact for most items that are manufactured. Vending machines have a range of acceptable weights for coins. Coins that don't measure up fall right through the slot. Manufacturing always has some variation. One has to decide how much variation is acceptable. A manufacturer of sledgehammers could tolerate a much wider interval of variability than a producer of fine surgical instruments. And I couldn't resist this cartoon when I saw it after I made the sledgehammer reference. Your view of statistics may be that it is used in surveys and studies involving various facets of human behavior or reaction to various things like drug studies and so forth. But it plays a huge role in quality control for manufacturing. Samples are regularly analyzed to ensure manufacturing specifications are consistent. Usually it isn't feasible to examine every item produced, so samples are used. If samples yield results that are unlikely, the manufacturing process is examined and tweaked to correct the problem. Now let's look at the effect of outliers on confidence intervals. The pasteurization process reduces the amount of bacteria found in dairy products such as milk. The following table represents analysis of the counts of bacteria in pasteurized milk for a random sample of 12 pasteurized glasses of milk. Suppose a student miscalculated the amount of bacteria and recorded a much larger result than the actual value along with the original data. What effect does this additional observation have on the 95% confidence interval? So here's the table. You can see that without the outlier, the mean was 6.41, the sample standard deviation was 4.55, and the confidence interval was 3.52 to 9.3. With the outlier, you can see that the mean was 7.69, and they told us that the result was larger, the count was larger than it should have been, so it's no surprise that the mean went up. The standard deviation for the sample went up to 6.34, and the interval is now 3.86 to 11.52. So with the outlier, the sample mean is larger because the sample mean is not resistant. We learned that in an earlier lesson. With the outlier, the sample standard deviation is larger because the sample standard deviation is not resistant, and we've learned that before. And with the outlier, the width of the interval increased from 5.78 to 7.66. And remember, the width of the interval we get by subtracting the two endpoints. Not only did the interval increase, the width of the interval increase, but the whole interval went up. So the low point without the outlier was 3.52 and the lowest point with the outlier was 3.86. Now complete Module 5, Part 2, Assessment of Learning. The password is confidence, all lowercase.